again. We are going to try multiplying numbers in scientific notation. Now, I've said in the past that scientific notation is really useful in the sciences. So in physics and chemistry, when you're dealing with things the scale of the universe or the size of a tiny atom, really big numbers, really small numbers, tiny dosages of medicine, of pharmaceutical drugs to give people. And often, I remember in my days doing physics in university, you need to multiply some of these numbers, do maths with them, to find the answers. So what if we had two numbers in scientific notation and we wanted to multiply them? What you could do is reorder them. This is 3 times 10 squared, so it's a big number, happens to be 300, times 4 times 10 to the power of 6, which is another big number, happens to be 4 million. We could reorder it so that the number parts, I'll call them, are together, and the power of 10 parts are together. So the 10 squared and the 10 to the power of 6 are together. There we go, now they're with their friends. Now we can recognize that 3 times 4 is 12. 10 squared times 10 to the power of 6, well, these are exponents. I'm multiplying these two exponents together. So I need to add these numbers, the 2 plus the 6, to get 8. Now this is correct that it's the same, but it's not in scientific notation. To be in scientific notation, this number needs to be between 1 and 10. That way, there is only one way to write a number in scientific notation, and we can be consistent. So I'm going to have to convert this bit into scientific notation. To do that, I can recognize that the decimal was here, and it moves one place to make it to the left. So this number is 1.2 times 10 to the power of 1. It's 1 because the decimal moved one place. And then I can copy the times 10 to the power of 8. 12 is the same as this. Okay, well now I've got 1.2 times, this is the same kind of thing we had before. A power of 10 multiplied by another power of 10, you add these exponents. 1 plus 8 gives 9. And now it is in scientific notation. Yes! Okay, let's try another one. This one, I'm getting this number in scientific notation and then cubing it. It might be, I don't know, the volume of a tiny cube of substance. I don't know, maybe a drug or a medicine or a molecule or a substance. I don't know. Anyway, I'm getting this number and I'm cubing it. You might remember if we've got a power outside the brackets and two things multiplied inside the brackets, each of those things needs to get the power. The 3 gets that power of 3, that cubed, and the 10 to the minus 3 also gets that cubed. Each of these things gets cubed when you've got a power outside the brackets. Now, to avoid confusion, I'm going to put some brackets in, because otherwise it looks like 10 to the power of minus 33, which is tiny. It's even smaller than an atom, if that's a measurement in length. So let's put the brackets in to show that it's this number cubed. The first part, if you've got your reference table of powers of 2 and 3 and so on, you can look it up. But otherwise, it is 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. And this part here, we can use the rule that if you've got an exponent outside, add an exponent inside, you multiply them together. 3 times 3 is 9, negative times positive is negative. Negative 9. We have the same problem that we had here, that this number isn't in scientific notation, which is frustrating. So we have to convert it to scientific notation. Because to be scientific notation, this first number needs to be between 1 and 10. So imagine the decimal point is here. I want it to be after the first significant figure, which is here. So it moves one place to the left. So it's very similar to this one here. 2.7 times 10 to the power of 1. I copy down the times 10 to the power of minus 9, because that was in the previous line, so I copy it down. And now we can do a similar thing that we did here to simplify 10 to the power of 1 times 10 to the power of minus 9. 1 plus minus 9. That's the same as 1 minus 9. And if you have 1, and subtract 9, you get negative 8. I like to imagine a number line. Should I draw a number line? Yeah, sure. Imagine that you had 0 is here. There we go. And 1 is here. And imagine that you went back 9 spaces. 6, 7, 8. There we go. Then you would end up at -8 on my very messy diagram I'm drawing on this trackpad here. There we go. Is this one done? Well, yeah, I've got a number times 10 to the power of something. And the number is between 1 and 10. Woohoo! We win! One last question to practice. This one is a fraction. And for fractions, whether there's scientific notation or other index law things, sometimes it's nice to split it in its parts. So let's split this into, just like we did here, the number part, 8 divided by 4, and the power of 10 part, 10 to the power of 5 divided by 10 cubed. And now we need to simplify. 8 divided by 4, if I simplify that part, it's 2. And 10 to the power of 5 divided by 10 to the power of 3, well, if I have a fraction, power on the top, power on the bottom, same base, I would do 5 take 3. And that is my new power. I probably could have jumped straight to the answer, couldn't I? Because we know what 5 take 3 is. I'm going to copy this exactly. Equals 2 times 10 to the power of 2. So isn't this so much easier? Imagine being a scientist and dealing with this as a scientific number instead of this. I would definitely say that has been simplified. To practice more questions like this, you want to try exercise 2C.1 and question 10. All right, I hope you got something out of this, and I will see you next time.